I'm Suman Tatiraju, Senior Manager. Um, Run an engineering team at NVIDIA working on Dynamo, which is a in-source distributed inference platform. This talk today is about like one big shift. What changes when the thing you are serving is an agent and not a chatbot? And how does Dynamo try to come up with smart solutions for this? And skip this slide. All right. Let's start with at a very basic level. A chat request is one shot and is stateless. Basically, a prompt in and a completion out. However, an agentic task is completely different. It's a trajectory. So you have an agentic task, which is like a loop where the model reasons, like think of all the green boxes as the reasoning boxes. And then it emits a tool call. The harness, in this example, you can think of it as a tool agent harness. It runs this tool call and appends to the response. And then it goes back again. The loop happens where now the LLM reasons, there's a tool call again, and the sequence goes on. There is also subagents which get spawned, and then they join back once they're done, which has its own trajectory. So the key thing that we see here is in an agentic task, we have many LLM requests interleaved with tool calls. And this is something that starts looking at some kind of a structure that we can exploit. If we look at what is the common thing that goes into each of these LLMs is a stable prefix. It could be a system prompt. It could be a repo context, or as we discussed, it was the prior tool output. There is a lot of prefix match that happens. That is one of the structure elements. The second thing we discussed is this tool call itself. The tool calls generally tend to be like, it could be like a shell command. It could be running long tests, or it could be like a web search. The tool call itself can range between like a few milliseconds to a couple of minutes. That's another thing that we can explore. There is a structural way of how agentic tasks work. First, a stable prefix. The second thing is a tool calling gaps along the LLM calls. The third is a very structure itself about how a parent agent spawns subagents. So there is like a parent and a child relationship. So there is that structure that we can explore. And the fourth one, I think somebody was just talking about like, what is the actual metric that we want to measure here when it comes to agentic tasks? It's not per request latency anymore. It's about what is the end-to-end run that the task takes, how long does it take, and we are trying to optimize for that. So the key takeaway here is agentic inference as structure. Some are GPU bound, which is the LLM turns. And then during the tool calls, the GPU is idle. So what happens to the KV cache that the trajectory was using? It's just sitting idle there when a tool call is happening. The same thing about subagents. When subagents exist, like for example, here, when we do a join here, the subagent is done. What happens to its KV cache? Should it actually stay in the GPU's HBM? Now, these are all the exploits that we will talk about in today's talk. Another way of looking at it is keep this in your mind, because this will keep coming back as I talk. Stable prefixes tool gaps, session gaps, and what is the actual objective, which is like the end-to-end task progress and not isolated request latencies. So this is a representative of improvements that we have seen through our experiments. Again, these are all experiments, and everything that we have done is available in Dynamo repo. And I will call out when there is an RFC or something that we are currently working on. But most of the experiments are already available. The three things that you will see is about scheduling, agentic hints, and cache policy. Let's talk about the first one, which is the scheduling. We saw there is that structure that current servers do not exploit because they consider them as individual requests. But what if our scheduler, as part of a router, also is session aware? It knows what are the subagents. It knows when tool calling will happen. Can we exploit that to optimize? And this is one of the experiments that we did with Thunder Agent. Thunder Agent is an paper, actually, where they discuss some of these techniques, and we implemented some of them in Dynamo, and we saw 16% improvement. The use case here was we were using a coding agent on a 8 H-100 node, H100 node, using coding agent, I think 10 trajectories and 36 concurrencies. It's an experiment which shows that this is the right way to progress. The other exploration that we did were agentic hints. I'm going to discuss everything in detail, but this is like the buff improvements that we have seen with agentic hints. We increased the performance of the number of queries per minute on shallow deep research by 3.3x. The third one is the caching policies, about what happens after a subagent is done. You evict its KV cache so that the parent agent's cache is still resident and we can use it. So that showed another 25% improvement on our KV cache hit rate. All these experiments show that we're heading in the right direction. So that's why at the end, I will actually present a roadmap of what Dynamo is doing for improving agentic task performance and serving. So to tie all of these, so think about what happens in a regular chat request. Like, there's no relationship between one chat request to another chat request. But with agentic tasks, we have trajectories, and they are linked between parent and child. We need to know for any kind of improvements that how are these requests connected? And for that, we have established what is called as a session identity. All requests in this task have the same session ID from which you can establish a parent-child relationship. Why was this needed? Every harness has its own identity. Like Cloud Code, Codex, OpenCode have their own HTTP headers for session identity. And they are unaware of Dynamo. So when you have a harness talking to Dynamo, what Dynamo does in its front end is it normalizes all the headers that it is getting into its own internal representation, basically mapping whatever Cloud Code, Codex, and OpenCode may have, or any custom identity harness that the harness may be using. We normalize it to an internal representation of our session ID. And this enables us to have the same representation across everything downstream, which is our front end, which we use for generating traces, replays, and profiling signals. The router now knows, like, okay, all these requests are now related to the same session ID, and it can actually figure out whether this request is for tool calling or just for an LLM. So we use this session ID everywhere downstream. And this is a very key aspect that we want to say here is like the identity connects the requests, but it doesn't do anything on its own. We leave individual components to decide what optimization they want to do given this information. So it's not necessarily like we are saying that it has to be done a certain way. We are only an advisory where we say, okay, these are all connected. Now it's up to individual components whether they want to act on. The same thing for KV cache layers. How do you reuse and prepare the existing KV cache blocks based on session IDs? And this kind of joins the whole picture of we needed a single identity to establish what are the different trajectories and runs for a particular agent task. The next thing that you look into is there is only so much that you can infer from the structure. We spoke about how there are gaps between tool calls, and there's this parent-child relationship between agents and sub-agents. But there's things that only the harness can know ahead of time. Things like, okay, is this task a parent agent, which is, let's say, it impacts UX, versus a background sub-agent whose priority is okay if there is some delay, but for something that impacts UX, the agent would know. So one way to give us hints during serving is via agent hints. So we have something called as the NVEXT agent hints for the harness to give us hints so that we can, based on this hint, make changes to our queuing and scheduling. It also impacts how we prepare our caches. So each of these I will go in detail now. So there are 3 hints that we currently support. One is priority. As I said, like the harness can easily tell us whether a particular trajectory is higher priority than others. And those agentic hints are basically request intents. They are only intents. The infrastructure chooses the final actuation. The router uses this priority to reorder what's in the pending queue when there is pressure, so that tasks with higher priority get queued at the beginning of the queue. The same priority is also sent to the engine schedulers if engines support this priority. The second one is the OSL. Harnesses know generally like what is a good OSL estimation. The prompt could be like summarize in 100 words or something like that. And that intent is now passed on, which we can use it for capacity tracking. The KB warm-up, which is like we may want to speculatively pre-fill our KB cache blocks if the agent gives us a hint. Again, these are on top of additional structural information that we already have from the nature of how these tasks are scheduled. These are additional hints that help us. Remember the agentic hint that we gave, which I showed earlier? This is the one, which is the priority, which we are using for establishing priority reorders for that router queue. The code for this is already there in today's code, and we have tested it out across all 3 engines, VLLM, TRT, LLM, and SGLang. So you should be able to test it out from KeepUp. So when we established the single session identity, now how do we make improvements without observability? So I think the fundamental thing that we are trying to fix here is like, given this session identity, are we able to generate traces which have all this information about, are we in a tool calling phase? Are we in an LLM phase? If we are in the LLM phase, then is it the pre-fill? It's the decode. What are the metrics? We can now establish using the session ID, request traces with serving metrics, tool intent, and parent and child structure. Now, this diagram shows an example of what we as by using one of the deep research trees, which clearly shows that when do we have in this agentic task, when do we have a tool call, which is doing a web search versus an LLM call for reasoning? And you tie this whole thing up to get a clear view of where your latencies are. Once you have an observable trace, now it's about, now what do you do with it? It's very important to understand that generating this trace could have been done by the harness emitting you events. Even if the harness doesn't emit events to Dynamo, Dynamo can still figure out through its metrics and also figuring out from the session IDs, like when did a cool tool calling happen? It's basically, it can infer from all of this. So we have built a smart system where even if harnesses don't send us events, we will be able to show end-to-end agent graph. Now, what do we do with this? Now that we have generated traces, this is where we run this iteration about how do we now change routing policies or scheduling techniques. And then instead of having to use GPUs, Dynamo has something called as the Dynamo Mocker, which simulates the LLM and SG-line scheduler and also cache management. So instead of now using your precious GPU, once you have captured your traces, you can now replay. So once you capture your session traces, you normalize, Dynamo normalizes them to mooncake hash format, replaces your token contents through and replaces them with token hashes, improves security, and also enables you to look into the prefix cache hits and all of that. So you can replay these traces and rerun them live against a particular GPU or against a simulated engine via Dynamo Mocker. That reduces the cost. You can actually iterate very quickly on your engine and scheduler policies. The agent traces that we have collected are all connected because of the session ID that we established. Otherwise, they would have been individual traces and we wouldn't have been able to link them up. It also is going to show you the exact structure of your agent. And this iteration step is going to help you with improving your engine and scheduler policies. Remember the slide where I showed about Thunder Agent router? Thunder Agent router is actually a router which is session aware. So it can now schedule worker requests based on the understanding that it is no more a generic request aware, but is actually session aware. To enable that, in our experiments, it ended up having an additional queue, which is like shown in the purple here, in addition to the current router queue, which was request aware. It was just an experiment to showcase whether a session aware route would actually improve anything. So that was our current implementation. We had an additional queue. Now that actually confuses the route aware. We have now a separate path for request aware and separate path for session aware. We are now moving towards a single admission gate inside our router, which uses both the session state and the engine pressure to schedule tasks. Again, this is where it's an improvement that we are going to get so that we have one single admission gate, which is both session and request aware. And then it will schedule a bounded active set for the engine. This is currently that the team is currently actively developing. The remaining part, the previous parts of session identity tracing and replay, all of that are already done and available in. This is something now, the next few slides I'm going to discuss are about the future and the RFCs that we have proposed. We spoke about structure, we spoke about agents, hints, agentic hints. Now we are talking to the next layer of KB cache intents that we can provide inference engines. Inference engines are stateless and they remain authoritative in this mechanism. What we are trying to propose is a KV orchestrator, which has the knowledge from the router of what are the tasks or the requests which have belonged to a particular session. And they produce intent related to caching. Now I'll speak a little more on how does caching actually come into picture. Remember the third slide where I showed that we were able to get about 25% better cache bit rate. It's coming from one of our experiments where we try to see there are a couple of ways we can do here. If you remember, there is this LLM running and then there is a tool call that happens after that. Now, during this tool call can be a few minutes long. So what can we do during this time when the trajectories KV cache is resident at GPU? Can we actually make the KV cache now go to a lower tier of the cache instead of being resident inside GPU memory? Can we, at the end of subagent, evict KV cache? So all of this requires some intent that we can send to the inference engine. So the team is currently working on APIs that we can work and give this agentic KV intent to the inference engines so that inference engines can now make authoritative calls, or they may say, okay, this is just a hint, we may ignore it. But at least we want to showcase what is the improvement that we can get through this path. The final control of scheduling and caching at the end always lies with the inference engines, and they continue to remain authoritative. We are adding layers on top of that to provide these hints given the structure that we can exploit. This is the one that I was talking about. Now, what are the intents that we can provide the inference engines? This is about placement and life cycles. One is to share, which is like we use a prefix from another worker. So we have shown that the very first structure that is present across calls is the shared prefix. And if we can share it across multiple runs, that's the way we can get best benefit for your KV cache blocks, which are already calculated. What happens when there was a subagent and now we are joining back to your parent agent? At that point, what happens is we can prefetch the parent agent's cache and then continue instead of like either recompute, because how can we prefetch? We could have demoted at the time of when the subagent comes in. We can demote the parent agent's KV cache to a lower tier, and when the subagent joins back, we can prefetch it. So we're trying to see how we can keep our KV cache resident inside HBM, knowing that there is a structure. The same goes about protecting KV. One is pinning, where we do bounded protection for a valuable prefix. And then there is a retain, which is like the bias eviction order with relative priority and duration. Now, these are all hints. It is up to the inference engine to either support it, or even if it is supported, it may not, like based on how you configure it, it may not act on it. But to enable all of this, we need to tag each of the KV blocks with the session ID so that we can do all the lookup for the router to give these intents. That's something that we are currently working on. And we will know once. I think the first experiment that we did was with SG9, which I want to show you, like how did we get that 25% hit rate. This was the sub-agent lifecycle that we saw. The parent becomes idle and becomes a demotion candidate. So you can demote the KV cache to a lower tier. And then at the time when the tool sub-agent closes, you can prefetch the parent and the child KV can get erased. This was the experiment that showed that 25% extra cache hit rate. These are all the RFCs that we have proposed, which take care of all the or exploiting all the structure that is present. So, in today's mainline source code, you have the identity, which is the session identity I spoke about, which is a header native. The observability part, which is about request tracing and replay. We're currently doing the schedule, which is like the admission control, which is both session aware and request aware. There will also be sticky session awareness here. And the RFCs that we have is like for the caching layers. Now, can we optimize for knowing the structure? How do we optimize for KV cache? At the horizon, we expect that we can bring in your own routing algorithms and profiles. But then the goal is to have one single session identity and observable policies. The engine still is the authority here. These are all hints that engine can. Thanks. And I'm open to some questions now. But if you want to reach out to me, that's my email address. And please feel free to connect on LinkedIn. Thank
you. It's good to see a lot of good stuff being added to Dynamo to support agent development. There's a few good questions. I brought up one for you to take a look and answer. Does this mean the agent hints are not explicitly sent by the harness, but instead infer from session context to inform the routing priority?
The agent hints are explicitly sent by the harness. We expect them to send the harness, especially the prioritization, the OSL, all of that. They are sent by the harness to Dynamo. Dynamo, as I said, like Dynamo can figure out the structure, but it won't know whether this was higher priority than that. The agent harness is the authority there, which can tell us. It can hint us that, hey, this is higher priority, and it ends up being important for your tasks end-to-end run. So
got it.
It can
cool. Thank you.